We swapped in a cheaper, faster model once because it looked fine in the demo and cut the bill. Somebody switched everything to a smaller model to save money, and in the live demo its answers came out fast and looked just fine. The whole room nodded and the savings on the slide were real, so we shipped it that afternoon. A week later, the complaints started, subtle ones, answers that were technically fine and quietly worse than before. So we finally ran the new model against our golden set, the fixed list of hard cases we already had the right answers to. It scored lower than the version we replaced. The demo had flattered us and nobody had measured the thing we actually shipped. That's an optimization failure, and optimization is a big, heavily tested slice of this exam. So let me take it apart the way the exam will ask you to. Every change you make to a live system is a bet that you improved it and didn't break something else. The architect's job is to never place that bait blind. By the end of this, you'll know how to run a test that tells you the truth instead of flattering you. You'll also learn to trace the problem down to the exact layer it lives on and to cut cost without gambling the quality you already have. And we'll answer the meeting question, how you tell a real improvement from a change that only feels like one. Start with the word optimize because it hides an assumption that ruins people. To optimize means to make something better, and better only means anything if you can measure it. You measure the before and the after against the same fixed ruler. That ruler already has a name from the evals episode, the golden set, the curated list of real cases with known right answers. Before you touch anything, you run the current system against it and write the score down. That number is your baseline. The official guidance is blunt about this. You define what success means and build the evaluation before you start tuning. And you state the target as a measured improvement over your current baseline. So a sharp demo answer isn't measurement, and neither is a chart that ticks up. Treating a feeling as measurement has a name, eval blindness. So let me show you the honest version of the test that meeting skipped. An A/B test is simple in shape. You run the old version and the new version against the same golden set, and you keep whichever one measurably wins. Because you weren't measuring the thing you shipped that afternoon, you were measuring how you felt about it. The reason to work this way isn't process for its own sake. It's that a scorecard can tell a real regression apart from random noise, and a demo simply can't. And there's one rule that makes the whole test mean anything. Change one thing at a time. If you reword the prompt, swap the model, and trim the context all in one release, and the score moves, you've learned nothing. You can't say which change did it. One change, then one measurement, and that discipline is exactly the kind of call the exam puts in front of you. These are original questions, written in the blueprint style, not real exam items. We eliminate on principle, so let's run one the way you would on exam day. A team wants an agent's answers to get better and proposes shipping a reworded prompt, a larger model, and a trimmed context all in one release. They plan to read the golden set score once afterward to see if it worked. Option A, run an A/B test that changes exactly one variable at a time, so each change's effect is measurable before it ships. Option B, skip the test and just move to the larger model since a stronger model is the safe bet. Option C, raise the temperature and the token limit to sharpen the output, then ship. Option D, ship the reworded prompt now because it reads better, and watch production for regressions. A is the only option that changes one thing at a time, so you can tell which change helped and which one quietly hurt. D is eval blindness, shipping on how it reads with no signal that it actually helped. B is scale, not strategy, a bigger model bait with no measurement behind it. C is a knob that tunes how the output wobbles instead of designing the change. The answer is A. Now the second skill, because before you can optimize a problem, you have to find where it lives. When a system gets worse, the amateur move is to grab the nearest knob and start turning. Usually that's the prompt, because the prompt is the thing you can see. The professional move is a diagnosis tree, and it has 5 suspects. A bad answer can come from the prompt, from the context you fed the model, from retrieval pulling the wrong documents, from the wrong model for the job, or from a tool that misbehaved. Prompt, context, retrieval, model, tooling, that's your list of 5. Your first job is to find which branch the cause is actually on. You read the symptom like evidence. So if it only breaks on very long inputs and gets worse, the deeper the important detail sits that points at context. The fix there is chunking the input, not rewording the prompt. Reaching for the prompt when the cause is retrieval has a name wrong layer fix. So does reaching for a bigger model when the cause is context. It's one of the exam's favorite traps because the wrong fix always feels productive. Here is a diagnosis question in the exam style. An agent that summarizes legal contracts has started dropping clauses near the middle of the longest documents as the contracts under review have gotten longer. The model, the prompt, and the tools are all unchanged, and it only happens on the very longest inputs. Option A. Upgrade to a more capable model so it can handle the documents. Option B. Add a line to the prompt telling it never to miss a clause. Option C. Treat it as a context problem and chunk the contract, summarizing it section by section instead of stuffing the whole thing into one window. Option D. Add a logging step that records which clauses were summarized so misses can be reviewed. Read the symptom because it hands you the branch. It tracks with input length and with where the clause sits. And that's the signature of a context problem, not a model or a prompt one. C fixes the layer where the cause lives, cutting the input down so nothing important gets buried in the middle of a giant window. A is a wrong layer fix because a better model in the same oversized window still loses the middle. B is louder, not explicit, because asking more firmly doesn't let the model see what it structurally can't hold. D is compliance theater. A log of the misses documents the bug without removing it. The answer is C. Now the third skill, cost, and there's an order to it that keeps you safe. You optimize cost from the outside in, and you start with the moves that change nothing about what the model outputs. The first is caching. If a big chunk of every request is identical, a policy document or a long instruction block, you put that static part first and cache it. After the first call, those cached reads are billed at about a tenth of the normal input price for the very same content you were paying full for before. The second is routing. You send the easy high volume work to a smaller, faster model, and you keep the top model for the calls that genuinely need deep reasoning. The third is batching. If the work isn't time sensitive, you send it through the asynchronous batch path, which costs a good deal less. Cache it, route it, batch it, and notice what none of those three did. Not one of them changed a single word of the output. That's the whole point. You can take a heavy workload and cut the bill roughly in half without ever risking the quality you already measured. Only after those safe wins are used up do you touch the quality bearing config, the prompt wording, the model tier for hard calls, the context you trim. The moment you touch those, you are back to A/B testing against the golden set. Because the trap on this branch is premature optimization, changing the risky things first when the free wins were sitting right there. One more, and it ties the cost order together. A high volume classification service is over budget. Every request uses the top tier model, sends a large instruction block that never changes, then a short input, and the results aren't time sensitive. Option A. Move to a larger context window so more fits into each call. Option B. Lower max tokens and temperature to cut spend. Option C. Rewrite every prompt to be shorter before measuring anything. Option D. Cache the static instruction block, route the simple classifications to a faster, cheaper model, send the non-urgent volume through the batch path, and measure the bill before and after. The stem hands you three gifts: a static block that repeats, work that's simple, and work that isn't urgent. Those map exactly onto caching, routing, and batching. D takes all three safe wins and measures the result, cutting cost without touching a word of the output. The change one thing rule guards quality bearing changes, but these three change no output. so you can apply them together and check the win on the bill alone. D is the answer. Is scale not strategy? A bigger window is just more capacity for a bill that's already too high. B is a knob that nibbles at spend while ignoring the huge repeated block sitting in every call. C is premature optimization, rewriting quality bearing prompts before measuring anything. The riskiest move first when the free wins were right there. So back to the meeting and how you tell a real improvement from one that only feels like it. You measure it against a fixed ruler you set before you change anything, and you let the golden set decide. Because the demo will flatter you and the users will pay for it. When something breaks, you read the symptom, name which of the 5 layers the cause lives on and pick that branch instead of the nearest knob. When you cut cost, you take the free wins first, cache it, route it, batch it, and you touch the quality bearing config last with a test running. Through all of it, you change one thing at a time, so every number you report is a number you can defend. A good optimization isn't the one that felt best in the room. It's the one you can prove didn't break what already worked. So find the constraint, name the principle, and pick the option that breaks nothing. Next, we move from making the system better to keeping it safe. That's the guardrails and failure modes that decide whether it should ship at all.